And he is here in this room. Great. Of course, it's great to be here. People from Lima possibly underestimate this possibility of coming from far away to here and to see this nice city. It's great that IMCA exists, and people in IMCA are able and are willing to organize events like this one. This is already almost not possible in many other places. And of course, it's great that this conference is dedicated to Jean-Pierre. Of course, I know that this is not your birthday today, but still, I don't know what to say. Happy birthday. And please remain full of energy as always. Do good mathematics. Travel, visit other continents. This is great, and I hope to be able to meet you at some other continent as well, very soon. Thank you. So, okay, today I'm going to talk about error bounds and metric subregularity. Those who work in variational analysis know that these two things are very closely related. Error bounds for real valued functions and metric subregularity of set-valued mappings. The definitions are very similar. The criteria for these properties are very similar. And I'm going to demonstrate the similarity a little bit further. The tools which I'm going to use here, slopes. Primal space slopes are very well known, and they have been used for characterizing error bounds at metric subregularity and metric regularity for many years. Today I want to introduce dual space slopes and recommend them for use in applications and other things. Error bounds, metric subregularity, these are theoretical things which are very widely used in variational analysis, but they also have important practical applications, and actually error bounds were introduced many years ago for actually characterizing convergence rates of numerical algorithms. So these things are related to applications as well. Of course, I will remind the definitions and I will remind the criteria. Please do not expect new striking results in this presentation. I'm just trying to bring some order in what other people do and expose some important, from my point of view, things which are usually hidden in the proofs. The outline of my presentation, I will remind the concepts of error bounds and slopes, and I will also talk about a well-known problem. Metric subregularity theoretically can be seen as a particular case of error bounds. But on the other hand, the criteria of error bounds, which are very well known, cannot be immediately applied for characterizing metric subregularity of multifunctions, because the function which appears in this property is not lower semi-continuous, even if the set-valued mapping is closed. And the criteria, existing criteria for error bounds, usually assume that the function is lower semi-continuous. So in the second part of my talk, I will suggest some extension of this definition of error bounds and the criteria in such a way that after this extension, the case of metric subregularity will be covered. And in the last section, I will really talk about metric subregularity or metric Q subregularity, the Hölder analog of this property, depending on how much time is left, but I'm afraid not too much. This is the definition. So, given a function, an extended real-valued function, defined on a metric space, given a point where the function is 0, the value of the function is 0, we are looking for a set of solutions of this single inequality. Very simple problem, but with numerous practical applications. So, if a point doesn't belong to this set, it would be good to have some kind of estimate how far this point is from the set of solutions, and to have this estimate in terms of the value of the function itself. So f plus here has the usual meaning, maximum of f of x and 0. And I'm talking about the local property. This inequality holds for some positive tau and for all x near x bound. This is error bound, local error bound. Okay, so this is the property. This is an illustration, two simple functions. In both cases, this set SF is the negative half line. In the first case, we can get this estimate, this linear estimate, and even we can take tau equal 1. It's not difficult to check. In the second example, we can't get this estimate because f of x goes to 0 much quicker than x goes to 0 from the right. When we are dealing with this property, you can easily see we are not using the linear structure or anything like this, so everything can be done in the setting of an arbitrary metric space. And the property of metric subregularity, which I'm going to talk about in this last part of my presentation today, is defined here. It is defined for a multi-function, for a set-valued mapping between metric spaces. Given a point in the graph, we say that f is metrically subregular at this point. Again, if there exists a number, a positive number, such that this inequality holds locally. This is a weakened version of a more famous property, metric regularity, when y bar is fixed. If it is not fixed, it is metric regularity. It is also well known that this property of metric subregularity is equivalent to another important property, calmness, for the inverse mapping. And just looking at the definition, it is obvious that this property is equivalent to local error-bound property of this function. So it looks like this can be considered as a particular case of error bounds, but unfortunately, as I mentioned a few minutes ago, the existing criteria of the well-developed theory of error bounds cannot be applied directly for characterizing this property, because this function, this is one of the reasons, this function is not in general lowest continuous. Now, a list of important people, well, some of them are important, involved in this research. Some are much less important. And if you find that some important name is missing, tell me please, and I will get it here. The property, this one, the property of error bounds, can be equivalently characterized using this constant, which I'm going to call error bound modulus. So the property is equivalent to this constant being strictly positive. And it is not difficult to see that this is exactly the supremum of all values tau, such that this inequality holds. The objects, the tools which can be applied for characterizing error bounds. For many years, this concept has been used for characterizing error bounds and many other properties. It was introduced more than 30 years ago, And again, everything is in metric spaces, no linear structure. This is basically the maximal rate of descent of the function at the given point x. Here plus has the usual meaning. Of course, this is a local characterization. And now I'm going to introduce a non-local version of this slope. Here and later I will use this sign of rhombus for non-local constants used in this report. Basically what we have here, instead of lim sum here, just sup. And another thing is we have plus here. We don't have plus here, but plus is here. This is because we are looking for solutions of that inequality, f of x less than or equal to 0. So 0 is critical, but in principle we can use some other value here as well. And because of this plus, although this is non-local, supremum over all u, this u can't be too far from x. So this is non-local, but at the same time u cannot be somewhere too far because the distance is in the denominator here, and if u is too far, the denominator is big and the value is small, and we're looking for the supremum. So it can't happen. Now, strict outer slope and strict uniform strict slope. What do we have here? When characterizing error bounds, in particular, it's not enough to compute just this constant. We must know values of slopes at all points nearby. So it is convenient to use something like this. Here we have lim inf over all x going to x bar. From outside, f of x is greater than 0, but is going to 0. And this explains the word outer in the definition. And the word strict corresponds to the fact that when we consider the whole bunch of slopes at nearby points, what we get as a result gets some properties of the strict derivative. This explains the terminology, and absolutely the same thing here. Okay, so these are the definitions. And f of x bar, yes, f of x bar is 0. It was on my original slide. Okay, so basically f of x goes to f of x bar. Okay, and it is also obvious that we have this inequality. And it follows, of course, from comparing these two things. This thing is greater. It holds for these strict constructions as well, so we have this inequality. And this actually explains why local constructions can be used in characterizing error bounds in sufficient criteria. So you will see that this is the main object, and this second one can also be used as a sufficient condition, because if this one is positive, then automatically this one is positive. Okay. The first primal space criterion for error bounds. The first part of this theorem is this inequality, which is for free, nothing to prove. It just follows from the definition, and it is a necessary condition of error bounds. If this is positive, then this constant is positive as well. The second part of this theorem is much more important. If we additionally assume that both spaces are complete, and this function is lower semi-continuous near x bar, then these two constants coincide. And this is actually a necessary and sufficient criterion for error bounds, and the main one. The other criteria are consequences of this one. And for instance, we can use the local strict slope, which we had on the previous slide, for formulating sufficient conditions for error bounds. This is more or less the whole theory of primal space error bounds criteria. Dual space criteria are very popular in this research and in many other areas, to use dual space criteria, of course, we need linear structure. Now X is a normed linear space. The main tool is the Fréchet subdifferential. This is a reminder of the Fréchet subdifferential. And another constant, which I suggest calling subdifferential slope, basically the distance from 0 to this set, subdifferential slope. Without using this notation and this terminology, of course, this thing has been in use by many authors for several years. An interesting thing is, okay, I suggested to call it subdifferential slope, and 2 years ago here at the previous meeting of ISORA, I think it was here, Stephen Simon mentioned to me that 10 years before he used this constant, and he also called it differential slope. So for me, it's a very positive thing, showing that possibly my terminology is in the right direction. And Y slope, basically, it plays the same role as the corresponding primal space slope. It's also local, and they are closely related, and this is what I'm going to mention. Strict outer subdifferential slope is defined in a similar way using the same lim inf. Again, just knowing this constant is not enough. We need to have an estimate for all slopes nearby. This simple proposition, if we live in an Asplund space, then the strict slopes, primal space and the dual space, coincide. And this explains why this second one is in use for characterizing error bounds. And this is basically the full standard theory of error bounds. And these things, they can be found in many papers, but not in this terminology. Now an extension. What I suggest is to allow f depend on two variables. So f is defined on a product of two metric spaces. Again, we have this inequality. This is an assumption. This equality. This is an assumption. But the variables play different roles. X remains the main variable, and y is something auxiliary. Two assumptions. If y is not equal to y bar, then f of x bar, xy is positive. So it means that the solutions of this inequality can be found only when y equals to y bar, which is written here. So it doesn't matter whether I write y bar or y here, thanks to P1. And the second assumption is this lim inf is positive as f goes to 0, which means that when f goes to 0, y goes to y bar automatically, and it goes sufficiently fast compared to f of x bar. So just these two assumptions, nothing else. And we are again looking for solutions to this inequality, and we are looking also for estimates of this kind. And this is an extension. F has a local error bound property. At this point, if there exists a constant tau such that this inequality holds. And now look, I require this inequality to hold locally with respect to x, but globally with respect to y. Nothing new, as I said. In proofs, people use this type of things, but normally they're hidden somewhere in the proof. I am trying to expose them. That's basically it. And all criteria can be easily extended to this slightly more general case. If it happens that f doesn't depend on y, we obtain exactly what we have in the standard setting in terms of definitions and in terms of criteria. So the error bound modulus can be defined this way, and the property is equivalent to this constant being positive. Now, a trick which has also been used by many authors, we have two spaces, and we don't have to always use the standard distance. It is sometimes useful to have this non-symmetric distance depending on some parameter rho. Some people prefer to use sum. I prefer to use maximum here. It's not that important. Okay, so having that, the distance depends on rho. We can define the rho slope in the usual way as a function of two variables, just using this distance. Strict slope, I will omit alter now, because everything is alter in my presentation. But it is alter, because f of x bar is positive. I can't write just lim inf. I have to separate it into lim and inf, because rho is also here. The metric actually changes. Non-local slope is defined in the usual way, again depending on rho, and rhombus is here, the usual definition. Uniform strict slope is defined in the usual way, again, so nothing surprising. The inequality, the same inequality holds. So basically everything can be extended to this setting, including the main theory. Again, we have this inequality, which is for free, and in complete spaces under the lower semi-continuity assumption, these two constants coincide. So everything can be extended. A little bit of difference in the dual space setting. When both spaces are non-linear spaces, subdifferential slope is defined as infimum only of the x star part, the first part. The subdifferential, of course, elements of the subdifferential have two components. We are looking for infimum only of the norm of the first component, assuming that the second component is small, up to rho. So having this, we define the strict subdifferential slope in the usual way. Again, the same combination, and rho is also here. And we still have this proposition in the Asplund space setting. I think I missed mentioning this. In the Asplund space setting, we have this equality. Okay? I want to mention one more thing. In my question, which I asked Mark in the morning today about limits, what I meant, in principle, we can use limiting subdifferentials here in finite dimensional spaces. In infinite dimensional setting, it's not so easy to deal with limits. We need some compactness assumptions, etc. But here, when we are working with constants like this one, the lim inf is in R. No problems in the real line. No problem with limits, and everything is working. This is what I meant when I said that I didn't like limiting objects very much now compared to how I liked them, say, 20 years ago, 30 years ago. Oh, more than that, unfortunately. Sorry. Anyway, so we have the full theory, but I don't have much time. This is the main problem. So subregularity and even Q subregularity. The setting of metric spaces, the set-valued mapping, and Q between 0 and 1 included. This is the property. Compared to usual metric subregularity, we have Q here. It's easy to see that this property is now really a particular case of this extended version of error bounds for functions of two variables. I suggest defining the function this way. And again, this is nothing extremely new. Many people used this trick in the proofs. Now I want to expose this thing. And it is easy to see that this SF set for this function, the only inequality, is exactly f minus 1 of y bar. So this allows us to use all the definitions, criteria, and apply to this setting and to really characterize this property of metric Q subregularity. The subregularity modulus of order Q is defined this way. This is a particular, this is actually a realization of the corresponding modulus for F. Non-local slope can be defined this way, and this is the same definition but just applied to this function. Uniform strict Q slope is defined in the usual way, the same way. These are realizations of the corresponding definitions. So we can use slopes for set-valued mappings as well. This local slope, there is no Q here. It doesn't depend on Q actually, just the definition like this. The strict portion, the strict constant depends on Q because Q is here. It is given here explicitly. We have Q minus 1 here. It is actually just simple calculus to find out that this is what we need here. And if y goes to y bar, this goes to 0, but Q mi is less than 1. So this is actually in the denominator. We have something going to 0 in the denominator. This means that we can allow this thing to go to 0 as well. So this is an extension and it can work. The inequality is like this. Now we have Q explicitly here. We don't have it here, but we have it here. And strictly speaking, this is not the realization of the corresponding constant for F. This is the realization. But since Q is a constant, which is always positive, I removed it from here. We are comparing just whether a constant is positive or not, so Q doesn't play any role, but it does play the role when we want to get quantitative characterizations. So Q is there. The theorem can be formulated like this. Just one remark. In the original theorem we had equality. For set-valued mappings we can't have equality, unfortunately, and this can be easily explained, but I don't have time for these explanations unless someone asks me. The dual criteria can be formulated in terms of co-derivatives. The co-derivative is defined using the Fréchet normal column. This is a reminder of the definition. And one more tool is needed. This one, so-called duality mapping, given V in the original space, not 0. This is a set of all unit elements from the sphere such that this equality holds. So having this, subdifferential slope can be defined, in of course a non-linear space setting, can be defined like this. Rho is here and rho is here. This is this duality mapping, and this is precisely what is needed, and possibly this is the only new thing in my presentation. The dual criteria for the metric subregularity property can be formulated using this strict subdifferential slope. Again, this part is a part of simple calculus. Here we have this subdifferential rho slope which doesn't depend on Q. But for symmetry, here we have rho. We have to multiply this rho by this term. So having this, we can formulate dual space criteria for this property as well. And I think it is new. If the spaces are S-formed, and the graph is locally closed near the given point, we have this inequality, and this explains why this constant can be used for formulating sufficient conditions. If this constant is positive, then automatically this constant is positive, and the main primal space constant is positive as well, and this is equivalent to the error-bound property. Now, I'm afraid I have to skip the details and okay, nothing to skip. All the details have already been said, and this is the list of references to things which were used in this tool. That's it. Thank you for surviving my presentation. I understand that it was not an easy job to follow all these numerous constants, but all of them can be found in these publications, and believe me, it's not that difficult. Everything is pretty simple.
Okay, some question?
Yes, please.
Yes.
I would like to go back to your property P1, P2. I imagine that if you focus on by function of two variables, is it that you have in mind eventually that this could be used for reformulation of other problem that is going to equilibrium, what is sometimes called equilibrium problem, looking to points where this f of xy is less or equal to 0 for points moving in a set, and by this way to provide error bonds for those reformulation of problem. I'm thinking, for example, of VI. You have the representation function for the VI, thus you can transfer this VI problem in terms of Y functions, and thus equilibrium problem. And thanks to your study, you will be able to provide some kind of error bound to the solution set of those problems. Did you have this in mind?
I didn't, but it's good that you said this. You asked the question and you answered it, which is a very good thing.
This was the introduction, because my question is, if I am thinking to those precise f, do they fit those P1, P2?
I hope so. As I said, I'm not very well familiar with variational inequalities, but you are an expert, and since you say that it can be done, I believe it can be done. What I really had in mind is the distance function. The distance function obviously has all these properties. And in the reformulation of the metric subregularity in terms of error bounds, I just used the distance function to the power q. But it's likely that you are right, and it can other areas of application.
This
I hope so.
Very useful to try to adapt this kind of error bound to provide some distance to solution set for reformulated problems.
Yes, I hope it's going to work, but I can't promise immediately that it will, and say tomorrow present clear interpretation. But if you keep reminding me, then I will possibly give some exact answer at next ISORA, for example. If the organizers keep inviting me. Please do.
Wait. Other question? No? So, thank you very much.